Oh, no. All right, it's a pleasure to welcome our speaker today. It's Thomas Koberda from the University of Virginia, and he's going to tell us something about Hamiltonicity of graphs via regs. Thomas, please.
Thank you all for coming. It's a great pleasure and honor to speak in this seminar, and it's nice to see some faces that I haven't seen for a while. So, yeah, so I'd like to talk a little bit about, as Ilya said, Hamiltonicity of graphs, is the combinatorial invariant of graphs via the study of right-angled Artin groups. And so a lot of this will be joint work with Ramon Flores, who's at Seville, and Dilaram Karobay, who's at CUNY. Okay, so in very general terms, I'd like to talk about three sides of a triangle. So at one vertex, we'll have combinatorics of graphs. So for me, graphs are always finite and simple, so they have no double edges and no loops based at a vertex. And group theory and topology. And so what I'm mostly interested in are the interactions between the combinatorics of a graph and the corresponding group theory, and also between combinatorics of graphs and topology, where I'll spell out a little bit more what I mean by this. So the actors that are going to be appearing here are going to be fixed as follows. So gamma will always be a simple graph. So with a set of vertices V and set of edges E. And so this is the combinatorial object that we'll be investigating. And on the group theory side of the triangle, we'll have A of gamma be the right-angled Artin group. Gamma, so I suspect that most people in the audience know what this is. I'll give a very quick definition in case someone doesn't. So A of gamma is generated by the vertices, and two vertices commute if and only if they span an edge. And in the topology corner, this is the topology will play sort of an almost incidental role, although important nevertheless. So insofar as topology is concerned, we'll be interested in the cohomology algebra of A of gamma with coefficients in some field whose exact identity is not really important, other than that it be viewed as a trivial module over A of gamma. And this is by standard methods in geometry of non-positively curved spaces. This coincides with the cohomology algebra of a certain cat zero cube complex called the Salvetti complex. So I won't belabor that point too much. Suffice it to say that it is an invariant of the group A of gamma. So I drew this very general triangle up here, and I said that I wanted to talk about some of these arrows, especially the highlighted ones. So let me maybe spell out a more precise question. How are combinatorial properties of gamma encoded in the algebra of A of gamma? And this, where here I always, when I talk about the algebra of A of gamma, I always mean here viewed as an abstract group. So the definition of the right-angled Artin group is always given in terms of a graph to begin with, and so that there are always vertices and edges that are part of the data used to write it down, but these are not. I mean, these are not intrinsic to the group. The right-angled Artin group generally has many automorphisms, and so really, I think of the right-angled Artin group stripped of its presentation, and to involve the topology, I can also replace by the algebra of A of gamma, maybe in the structure of the cohomology algebra. And also there's the converse question. So if we know something about the algebraic structure of A of gamma, can we conclude something about the combinatorics of gamma? Or if we know something about the cohomology structure of A of gamma, how is that encoded in a precise way in the combinatorics of gamma? Okay, so maybe I'll begin with some examples of ways that one can answer this question. I mean, I think that this question is vague and open-ended enough that there's probably no one completely satisfactory statement. I mean, so there are some sort of answers to this question which are almost too trivial. For instance, it's known that for instance, okay, so if I hand you a right-angled Artin group, then the defining graph is unique. So that is to say, if gamma and lambda, sorry, if A of gamma and A of lambda are isomorphic right-angled Artin groups, then gamma and lambda were isomorphic graphs. So this is due to Drom's. If one reads the math review, this is the reviewer points out that this was already known long before Drom's in the context of semi-free Lie algebras. Other proofs were given by Lucas Sabalka, but on the so this is somehow not a satisfying answer to this question, because one can say, okay, well, if anything that you can say about the graph, okay, so that's some property of the right-angled Artin group, and then the right-angled Artin group itself can be used to reconstruct the graph. And so, what do you want? But then that's somehow I find that very unsatisfying philosophically. So the sorts of answers to this question that I'd like to find will be of the flavor that I'll enumerate now below. So I'll start with some simple examples. So let's consider connectedness. So one of the first things that one might ask about a graph when one considers its combinatorics is whether it's connected or not. Okay. So if one starts with a graph that is disconnected, then one finds in the definition of the right-angled Artin group, oops, too far, that you have generators for each vertex, and the relations arise from vertices that are incident to a particular edge. And so if you have a graph gamma which is disconnected, then relations are concentrated within connected components of gamma itself. And so you have any relation so the relations that occur in A of gamma can be separated by their components. And so that can be rephrased as follows. So if gamma is disconnected, then A of gamma splits as a non-trivial free product. And that's a very easy observation from what I just said. The converse is not particularly difficult if one has the right tools, and is also true. So if gamma is connected, then A of gamma does not split as a non-trivial free product. So this is oftentimes attributed to Brady and Meyer. So I think the proof of this is really just follows from the work of Stallings characterizing groups with infinitely many ends. So if A of gamma splits as a non-trivial free product, then it has infinitely many ends. But then now if you start with a graph that's connected, then you can write it as a union of two simpler graphs, the star of some vertex together with everything but that missing vertex, and then you can build up the graph inductively and use some sort of induction on the number of number of vertices and argue that the number of ends for a connected graph, the number of ends of the right-angled Artin group will be either 2 or 1. So therefore the resulting right-angled Artin group will not split as a non-trivial free product. So that's all I'll say about that. Another example, which I find to be very intellectually satisfying, is the problem of hidden subgraphs or hidden subgroups. So one considers this very specific graph. Let's call it lambda, which is just the square. So there are two pairs of diagonal vertices which generate free groups of rank 2, and they commute with each other. And so A of lambda is isomorphic to direct product of 2 free groups. And so now if lambda sits as a full subgraph of a graph gamma. When I say full subgraph, I always mean that so lambda consists of 4 vertices inside of gamma, and every edge that's present in gamma is required to be present in lambda. So then if lambda is a full subgraph of gamma, then A of lambda is a subgroup of A of gamma by the map induced by the inclusion of graphs. Okay, and so I mean these 2 lines that I've written at the very bottom of this slide are true for all graphs, not just lambda equal to the square, but specializing to the case of the square, we immediately get that if lambda is a full subgraph of gamma, then A of lambda is automatically a subgroup of A of gamma. And so if you see a square inside of gamma, then you will have a copy of F2 cross F2 as a subgroup of A of gamma. Okay, so now on the other hand, one can consider if one has a copy of a direct product of 2 free groups inside of the right-angled Artin group, does that force there to be a square inside? And so that is much trickier than this observation about full subgraphs inducing inclusions between graphs. But it is true. So there's a theorem due to Mark Combinatorial and an alternative proof was given by Kim and someone that said that if F2 cross F2 is a subgroup of given right-angled Artin group A of gamma, then gamma contains an induced square. I should say, to keep consistent terminology, I'll say full square subgraph. Okay. And so in particular, a copy of F2 cross F2 cannot be hidden inside of gamma. It is if you know that A of gamma contains a copy of a direct product of 2 non-abelian free groups, then the defining graph had a square to begin with. Of course, there may be copies of products of non-abelian free groups which are not exactly conjugate into this particular square that you see, but the point is that there is a square, so the presence is known by some means. So that's I think what I think is remarkable about this characterization of squared subgraphs of graphs by right-angled Artin groups is that it doesn't generalize to longer cycles. So not generalize to longer cycles. So let me say a few words about that. So let's let C5 be the next cycle. So this will be the pentagon graph. So this is the right-angled Artin group on C5 is one that is very interesting to geometric group theorists because it contains closed hyperbolic surface groups. And finding closed hyperbolic surface groups inside of other right-angled Artin groups is a very important and not completely solved problem. And so because the pentagon graphs are a source of such subgroups, it's an interesting problem to decide whether or not you can hide these subgroups in interesting ways, in ways that you can read them off from, say, the defining graph. And so it turns out that you might not be able to see a copy of the pentagon, even if the right-angled Artin group contains the right-angled Artin group on the pentagon. So this is a theorem from my co-author Sam Kim's thesis from about 15 years ago now. It says, if you consider the following graph, which is the triangular prism. So this is gamma. If you are bored in this talk, you can show that that gamma is isomorphic to the complement of the hexagon. Then one can check that C5 is not a full subgraph of gamma, but A of C5 embeds as a subgroup of A of gamma. So C5, A of C5 can be a hidden subgraph inside of a right-angled Artin group. And combining with one further result, one has that all right-angled Artin groups on longer cycles can be hidden in this way. So there's a theorem also due to Kim that says that for all n greater than or equal to 6, A of Cn can be realized as a subgroup of A of C5. And so combining with this embedding into the complement of the hexagon graph, all longer cycles can be hidden. So that's a nice opposition, I would say, to this result of Combitas.
Sorry, can you just remind me? I thought you guys also characterized when it happened. Though I thought that like you may not have a copy of C5, but then you have like the opposite graph of C5 or something. Isn't there some characterization like that?
No, we had a conjecture about that, but that turned out to be false, right? So okay. Yeah, so maybe I'll just engage with this briefly for, as a side note, right? So we had originally formulated this theorem that this conjecture that we call like the weakly chordal conjecture, which was supposed to say that that if you had a graph which was weakly chordal in the sense that every induced cycle of length 4 or more has a chord in it, then the corresponding right-angled Artin group doesn't admit does not admit a right-angled Artin group on a 5 cycle as a subgroup, or in fact any n cycle for n greater than 5. And this was shown to be false by Andrew Duncan and Ilya Kazachkov and Montserrat Casals Ruiz. So they proved that this is a theorem, I guess I'll just abbreviate their initials, Duncan, Casals Ruiz, Kazachkov. They say that if you take A of C5, then this embeds inside of A of, you take a path on like 8 vertices, I think was enough, either 7 or 8, but 8 is definitely enough. And then you take the opposite graph of that, then there's an embedding like this. And this is a counterexample to that conjecture.
Cool, thanks.
Yeah, in fact, one can generalize this result. It turns out that every right-angled Artin group embeds into the right-angled Artin group on a complement of a tree. A complement of a path is not enough, but a complement of a tree works for, so for any graph, you can embed it into the right-angled Artin group on a complement of a tree. Okay.
They did that, or that's some elementary observation, or?
No, that's a theorem. That was Kim and me also.
Okay.
Yeah.
I don't think I remember that. That's cool.
Yeah. Yeah.
Which paper is that in?
It's called like Antitrees.
Okay.
And yeah, or something like that. Yeah, Antitrees and right-angled Artin subgroups of planar braid groups. So something like that. Yeah.
Fine. I'll find it. Thanks.
Thank you. Okay. Yeah. So yeah. So maybe that's enough about hidden subgraphs and hidden paths. I'd like to do one more example because this chordality came up just in the discussion right now. There's an interest. So we know that subgroups of right-angled Artin groups can be extremely wild. So there are examples that are due to stallings and others, I guess, well, coming from combinatorial Morse theory that show that there are many subgroups of direct products of free groups, subdirect products of free groups that have a lot of exotic finiteness properties. There's a lot of work of Bridson and Miller, and I think the most famous paper on this is by Bestvina and Brady. So in particular, one can ask questions like, so given a graph, is the right-angled Artin group on that graph coherent? So is every finitely generated subgroup finitely presented as I guess the beyond finite generation? That's the simplest finiteness condition that one might hope for. And so there are subdirect products of the free group on of a direct product of a free group on two generators with itself, which are not finitely presented. Okay, and it turns out that one can actually completely characterize which right-angled Artin groups are coherent. So let me just state this as an example here. Coherence. So there's a theorem of Drom's that says the right-angled Artin group A of gamma is coherent if and only if gamma is chordal, which is to say, i.e., there are no full cycles of length greater than or equal to 4. So that's pretty cool. I mean, one can compare that to a characterization due to well, a characterization of which right-angled Artin groups occur as fundamental groups of 3 manifolds due to Gordon, Long, and Reed, which says that if a right-angled Artin group is the fundamental group of a compact three-manifold, then every component of the graph is either a tree or a triangle. Okay, so then every such graph is automatically chordal. And coherence is required for compact three-manifold groups by Scott's core theorem. Great. So that's maybe all I'll say about that. So then some more relations between the group theory of A of gamma and the combinatorics of gamma, which have sort of complete answers in terms of the motivating question that I stated at the beginning. So maybe if one looks at a graph, beyond whether or not it's connected, maybe the first, maybe the second question that one would ask is how symmetric it is, which is then precisely encoded by the size of its isomorphism group. So we look at isomorphisms. Okay, so now if we look at isomorphisms of graphs, then we note that the isomorphism of the underlying graph, or maybe I'll state this in terms of automorphisms of graphs. Sorry. I don't know why I said isomorphisms. Automorphisms of graphs. So if we look at an automorphism of a graph, then it gives an automorphism of the corresponding right-angled Artin group. It's very straightforward to see. Okay, and so perhaps the right place to look in trying to characterize graphs that admit automorphisms is in the group of automorphisms of the right-angled Artin group itself. Okay, so what might a candidate for such a characterization be? Well, one can note the following. So we have that aught of gamma always embeds in aught of A of gamma, and in fact into out of A of gamma. And further, one has some certain automorphisms of the right-angled Artin group that exist for any graph. So the full structure of the automorphism group of a right-angled Artin group depends highly on what gamma is. Certain transvections or partial conjugations exist sometimes and not other times, depending highly on the combinatorics of gamma. But one thing that you can always do is you can also do this vertex inversion. So you can, if you have any vertex in V of gamma, then you can send it to V inverse. Let's maybe call this inversion of V, and this inversion of V extends to an automorphism of the right-angled Artin group A of gamma. And so then you have this group isomorphic to Z mod 2Z to the number of vertices of gamma, which is a subgroup of out of A of gamma, and it's, or aught of A of gamma if you prefer, which is generated by inversion of vertices. And now the automorphisms of gamma and the inversions of vertices together generate a finite subgroup of out of A of gamma as follows. So if we look at inversions of vertices, together with odd of gamma. So this is then isomorphic to the semi-direct product of odd of gamma with this group Z mod 2 to the number of vertices of gamma. Okay. And so this group, in one of the last lines, the semi-direct product of odd gamma with Z mod 2 to the number of vertices, this is non-abelian. Non-abelian if odd gamma is not trivial. Okay. And so what these very elementary considerations that I've just carried out here show is that if gamma admits a non-trivial automorphism, then the group out of A of gamma, the group of outer automorphisms of A of gamma, contains a non-abelian finite subgroup. And it turns out that the converse is also true. The converse is, as may have become apparent as a pattern in everything that I've said so far, is oftentimes these theorems have one easy direction and one slightly less easy direction. So the slightly less easy direction is the converse here. So it says that that odd gamma is not trivial if and only if out A of gamma contains a non-abelian finite subgroup. Okay. So one of the reasons for considering something like automorphisms of a graph is because it's related to the isomorphism problem, which is very important in complexity theory. Although we know that for certain that it's that determining the problem of determining whether two graphs are isomorphic to each other or not is not NP complete. It's this quasi-polynomial times solution by the work of Babai. So, I mean, there are plenty of combinatorial properties of graphs which have the property that determining whether or not they hold in a particular graph is an NP complete problem. And so, for the sake of possibly applications, also it would be both intellectually satisfying and possibly quite lucrative also to figure out how to characterize such properties in terms of the right-angled Artin group. So let me talk about some examples of NP complete problems and the relationship to right-angled Artin groups. So okay. Number 4, I guess 5. Graph coloring. So by graph coloring, I mean, of course, this is the K colorability of vertices in a graph. So here a valid coloring is a valid K coloring is just a function from the vertices to a set with K elements, so that no two adjacent vertices have the same value under that function. So it's one can do these sort of classical sorting algorithms to decide if a graph is two colorable very efficiently, but it's a well-known foundational problem, a foundational result in complexity theory that deciding if a graph is three colorable or not is NP complete. So how might coloring of graphs be related to right-angled Artin groups? Well, one can begin as follows. So suppose gamma is k colorable. So then let gamma bar be obtained from gamma by inserting an edge between vertices of different colors. So when I say suppose, to make sense of this, okay, so I said suppose gamma is k colorable, and we should, I guess, fix the k coloring. So then you extend gamma to a graph gamma bar by inserting an edge between two vertices whenever they have different colors. Okay. And so then what one finds is you have a graph gamma bar with k subsets of its set of vertices, and these subsets have the property that they're independent, so they have no edges between them. And moreover, the graph gamma bar is the join of these subsets. So if subsets 1 and 2 corresponded to different colors, then every vertex of subset 1 is adjacent to every vertex of subset 2. And so then one can compute what the corresponding right-angled Artin group is going to be. So A of gamma bar is a direct product of free groups of rank n sub I, and you have that sum of n sub I is equal to the number of vertices. So that's, again, a fairly elementary consideration, and one might suspect that the converse is also true. Of course, the difficulty there is that if you consider arbitrary homomorphisms, even just arbitrary surjective homomorphisms to a product of free groups, there's not that much reason to suspect that such a homomorphism will respect vertices, in the sense that you know, in this equation, A of gamma bar is equal to this product of free groups. You have vertices of the graph on the left and vertices of some join of completely disconnected graphs on the right, and there's no reason to suspect that vertices should be respected by such an arbitrary homomorphism. So I'll just write an isomorphism here. But the converse of this, these considerations does hold. So here's a theorem also due to Flores and Karobai and someone that says that gamma is k colorable if and only if there exists a homomorphism A of gamma surjection to product of these free groups with the sum of the ranks equal to the number of vertices of gamma. And one can actually weaken the requirement that the map be surjective on the level of groups. One actually only needs it to be surjective on the level rational cohomology of these groups. Okay. Great, so let me now talk about maybe the last example of, I hope, a satisfactory answer to the framing question, and which will finally connect to cohomology in some way, and that's Hamiltonicity. So Hamiltonicity is a property that a graph may or may not have. So a graph has a Hamiltonian path if there's a path in the graph which visits every vertex exactly once, and a Hamiltonian cycle if it admits a cycle which visits every vertex exactly once. And so determining whether a graph has a Hamiltonian cycle or not is very difficult. It's also known to be NP complete. It's related to this traveling salesman problem very intimately. And I mean, I guess when one begins the study of graph theory, one learns about the 7 bridges of Königsberg and the existence of Eulerian paths or Eulerian cycles, which is easy to determine simply by counting degrees of vertices. And so the existence of a Eulerian path or Eulerian cycle is really just a local property of a graph. But Hamiltonicity, by virtue of it being NP complete, is really a global phenomenon for graphs, and that's what makes it so hard and so interesting. Okay, so let's try and understand Hamiltonicity from the point of view of right-angled Artin groups. So the characterization of Hamiltonicity really has to engage vertices and edges in a serious way. And if you want to talk about edges from the point of view of group theory, it's hard to do that. I mean, so vertices of a graph, I mean, that by virtue of the definition of the right-angled Artin group, they are elements inside of the right-angled Artin group. But edges aren't really. And that's where the cohomology comes in, because then edges in some natural way begin to correspond to second cohomology classes. So for this, we use the cohomology algebra of A of gamma. And I'm just going to suppress the notation for the field over which we do this. So this can be, you can do it over Q, you can do it over C, you can do it over a field with 2 elements. It really doesn't matter. So, the cohomology algebra is somehow is formal in the sense that the entire group A of gamma is determined by the first cohomology and the second cohomology, and the pairing from the cup product pairing from H1, tensor H1 to H2. It's actually, it's called I think one formality in the sense of Dennis Sullivan. Okay, so right, so what can we do with this? So if we enumerate the vertices V1 to Vn in gamma, then there are natural cohomology classes associated to them. So if we view them as elements of A of gamma, then in the abelianization of A of gamma, they form a basis for the homology of A of gamma with any ring of coefficients. So maybe let's say Z. And then homomorphism, you can take homomorphisms to Z simply by taking, you can build a basis for first cohomology with coefficients in Z simply by taking the dual basis. And so you have V1 star, V2 star, all the way to Vn star as a natural basis for H upper 1. Okay, and so this, what I said is, just formal linear algebra. Of course, there are nice sort of geometric ways of thinking about what these dual cohomology classes are in terms of intersections with hyperplanes and the solidity complex, but I won't belabor that point too much right now. Okay, and now moreover, we can enumerate the edges, say E1 all the way to EM. Right? These are the edges of gamma. Right? And we can write EI is maybe determined by this pair of vertices Vj, Vk. Okay. And there's a general structure theorem about the cohomology algebra of A of gamma that says that so there exists a basis, say E1 star all the way to EM star for H upper 2, such that Vj star cup with Vk star is equal to EI star whenever EI is equal to Vj and Vk, and Vj star cup Vl star is equal to 0 otherwise. So to say this in simple English, you just have generators of the first cohomology for vertices in the graph and generators of second cohomology for every edge, and two vertices cup to something non-trivial if and only if they are adjacent to each other in the graph, and the corresponding element of H upper 2 is the element corresponding to that edge. So then this allows us to talk about things like adjacency of general elements in the cohomology algebra. So you could take an arbitrary element of H upper 1, and you can cup it with some other arbitrary element, and if that cup product is non-zero, then you think of those elements as adjacent to each other, and if they cup to something that's 0, then they are not adjacent to each other. So let's say W1 to Wn be a basis for H upper 1 of A of gamma. And we say that, let's name it script B. So B is Hamiltonian if there exists a permutation sigma in Sn such that for all I we have W of sigma I cup W of sigma I plus 1 is not equal to 0. Right, so, and I'm sweeping one detail under the rug here, whether I let I be equal to N here, and you can or cannot, it doesn't, whether you're interested in Hamiltonian cycles or Hamiltonian paths, it doesn't really matter, so I just won't specify here. So observe the following. So if every basis for H upper 1 A of gamma is Hamiltonian, then gamma admits a Hamiltonian path. Okay, simply because we just take the basis consisting of dual vectors to vertices of gamma. Okay, and then what you've done is you've just reshuffled them in such a way that consecutive ones are adjacent to each other. And so you get from V1 star to Vn star via a path consisting of duals to edges. And so, yeah, so then this observation is then completely straightforward. Turns out that the converse is also true, but is significantly.
Sorry, why did you need every basis there? Why not just the existing basis?
So that what you're saying is true. That it suffices that there to be one particular basis, which is Hamiltonian. But for the converse to be true, you don't know which basis is the one corresponding to the duals of the vertices. So the H upper 1 is given to you as some abstract vector space. H upper 2 is some abstract vector space, and you have this pairing from H1 tensor H1 to H2. And what you should then have is that. So let me state the theorem and then comment a little bit more on your question. So gamma admits a Hamiltonian path if and only if every basis for H upper 1 is Hamiltonian. Right. So if you wanted to say, okay, so maybe it suffices to just have one Hamiltonian basis. That's unfortunately not good, because you could have like one central vertex which is adjacent to a bunch of other things, right? And then you just you cheat. You have the non-zero cup product be witnessed by edges emanating from this star, and then you can. It's not too hard to construct counterexamples which show that there are graphs which are not Hamiltonian, which admit some basis for H upper 1, which is Hamiltonian. But if it's true for every basis, then the graph had a Hamiltonian cycle. And so this involves some rather tricky linear algebra. Maybe in the last 2 minutes, I'll just state a technical lemma that arises in the proof of this, which it's sort of technical, but it's also just a result about all invertible matrices, which I think was kind of a fun little thing. So let's just let A be an element of GLN and F. Okay, and so we'll write it as Aij, where Ai and J go between 1 and n. So I is the row and J is the column. And so we'll build the 2-row graph of A. Okay, so the vertices are the rows, and and we'll say that row I is adjacent to row J if and only if there exists a K such that Aik plus 1, Aj plus 1. If this determinant is not equal to 0. Okay, so there's just this 2x. If you put the rows next to each other, you just have to find a 2x2 minor that's non-zero, consisting of adjacent columns. The fact that the columns are adjacent is crucial here. So we'll write this thing script G sub A. So here's a theorem. G sub A always admits a Hamiltonian path. So that's a very weird thing, I think, about just invertible matrices over any field. So yeah, okay, I guess it's 501, so I'll stop here.
All right, thank you very much. Let us thank Thomas for a very interesting talk. Thank you. So if there are any questions to the speaker, you're welcome to ask them now.
So in practice, how verifiable is this?
How verifiable is what?
If you wanted to actually figure out when these things have Hamiltonian path, like how?
Oh yeah. So like, could you like use this theorem to like check if a graph is Hamiltonian or not? You could, because so presumably the data that you'd start with is like some group, right, that is finitely presented, and well, let's sweep some computational things under the rug, such as like actually computing H upper 2 and the cup product pairing. So let's say that you know what H upper 1 is over a field with 2 elements and H upper 2 is over a field with 2 elements. Then this is all a finite set of data. Okay, and so then you're computing, you know, finitely many cup products, right? And then you can exhaustively check all permutations and see, okay, is this particular basis Hamiltonian or not? So I don't think that it's particularly efficient. It's almost.
So
yeah.
That's actually what I wanted to ask as a follow-up question to Jason's question. So I'm trying to remember what's the computational complexity, the worst case complexity for checking if a finite graph has a Hamiltonian path. How difficult is that?
I thought it was NP hard. It's not NP hard.
It is NP hard. Yes.
It is NP hard. That's
yes. That is a theorem. It is NP hard. Yes.
But it's not NP complete, or is it not?
It is NP complete. Yes.
Yes. I see.
Wait, so it can't be too easy to check for this vector space.
Well, yeah, it shouldn't be. So I mean, you do have like exponential algorithms which you can implement on a given graph, and I mean, depending on what data you actually start with, this could be actually less efficient than just checking directly by just checking, you know, the list of vertices and edges and trying to find the Hamiltonian path or Hamiltonian cycle by hand. So it's implementable, but it's probably less efficient than the brute force method, just if you know the graph itself.
Okay. Very good. Are there any other questions? All right. If not, let us thank Thomas again. Thank you.
Thank you all. So Ilya, this is recorded, but I can also send you the notes if you want.
Yeah, that would be great. Yes. So
okay.
then,
I'll do that later today.